Okay, for this question, so those who have a problem with this kind of question, to solve this, you need is either you can identify which one is going to lose energy on and which one is going to receive energy, and then put it in equation as Q loss equivalent to Q gain. Okay, so then the trick is that whenever you do this, that the loss one on the loss side, the temperature will be inverted compared to the gain one. So what I mean by this is that, let's say this one is A, and A here. So this is B, and B. So then for the loss side is actually you're going to be like this, MA, CA. So if I were to break it down, so then it can be TA, not initial, minus TA final. So this on this loss side is going to be inverted as what been described in the your notes. Okay, and then CB will be exactly as the definition of that delta T just now, which is should be B final minus initial. Okay, so another way is that you don't need to think whether it is that thing going to be loss or gain. Okay, it's just a matter of that you're going to see which direction is going to moving, it facing to the face changing. Okay, so what I mean by that is that you don't need to have which side going to be loss or gain, or for this kind of case, for example, like when you only deal with the del T, the change of T without any latent heat involved, you can always just simply having everything added this way without concern whether it's going to be loss or gain, and then everything need to be equal to zero. The reason why here, what does it mean is not equal to zero? Because there's no net heat transfer outside or inside the system. So let's say if I were to deal with these three things here, so what does it mean? It means that I have a body of three objects here. Let's say one of them are 100 degrees Celsius, another one is maybe 80 degrees Celsius, and then another one, the last one, maybe 20 degrees Celsius. So what does it mean? So of course, when it reaches thermal equilibrium, it's going to reach one temperature where all these three bodies going to be the same. So to solve this equation is much more easy, because here you're probably not quite sure which yeah, of course the 101 going to be lost its energy, but 80 degrees Celsius, we technically we don't know. It might not lose energy, it might gain energy, but in the end it doesn't matter. The reason why I say it doesn't matter, it is because if we follow to this equation, then it's going to be easier for us to perceive what happening. But then again, if you want to proceed on that, it's okay, but you just need to be careful not to forget to invert this final and initial here. Okay, coming back to the why does it equal to zero. So the reason it is equal to zero, it is because of there's no need heat transfer outside of this box, this blue box. I make the blue, and this blue box, there's no heat going outside the box or inside the box, so that's why there's no the equal to zero. Okay, so how are you going to solve this equation? You just follow through the equation. M A and 1, we just put 1 here, C1 del T 1 plus M2 C2 del T2 plus M3 C3 del T3. Okay, and then this one equal to 0. The reason equal to 0 because all these three object here, we know that it's going to be there's a net transfer between these three objects, but there are no heat going outside. Q equal to 0 here outside, or there's no charge going inside. So compared to if I were to ask you what, okay, we just leave this one for a while. Then we're going to explain what I want to explain just now. Okay, coming back to here. So what are we going to do? We're going to just follow to the what the equation meant. So this is going to be T1 final minus T1 initial plus M2 C2. So T2 final minus T2, and then but let's see if you want to make it like that just now, is technically just simply, okay, I just complete this one, M3 C3 the T3 final minus T3, okay, and then the one equal to 0. Okay, so what does it, how does this thing, you can see it's going to be similar to this has been come in the notes there. It is by placing the one that we call it to be heat loss, let's say 100 degrees Celsius heat loss, then we put it on the other side. So it means that, let's say this whole thing here, this thing is technically, or maybe I can just, wait, instead of putting negative 0 there, maybe I can put it on this side, doesn't matter. Okay, so what does it mean? So then the how can I follow through this? Presumably that M1C1 here is the one, that the only one going to loss in heat. Okay, so then it's going to be transferred to the left lah. Well, it should be on the left side. That's what we understand from the equation given in the notes there. Okay, so what happened is technically it's coming from this same equation that I just wrote down right now. Okay, so because we know it to be at the left, so then if we move that, then we're going to have negative C1, then T1F minus T1, okay, and then everything else we're going to remain at the right side, and plus M3 C3 T3F minus T3. Okay, so then if you look at here, if I were to, because we have negative outside here, because the reason why, because we just move this one to the left. Okay, so then we have negatives. Then if I were to bring the negative inside, multiply the negative inside, then what happened here, then this thing going to be inverted. So the T1 become positive, as what we have just now is negative, and then the T1F, the final temperature, is going to be negative. So then we don't have a negative sign in front anymore. Okay, so that's why we have it arranged in this way, but technically still following to this concept is easier this way. Okay, so back coming back to, okay, so I'm trying to explain this, and then we go, maybe we can solve this one first, and then I'm going to give you another example in order to explain the one that I'm holding back just now. Okay, coming back to this question. Okay, let me just move this away, since that I can't simply cut it away, so just move it somewhere else. Okay, focus on this back. Okay, so coming to this, what we have here is that we have an ice cube. Okay, so first of all we need to understand why does the ice cube, what happened, and we try to imagine what's going to happen. Of course, the water going to be colder, and then the ice cube probably going to be melt. So then if ice cube going to be melt, we always it's good to have this diagram to get us a better idea, a clear idea, so then we don't mix up our equation later on when we construct one. Okay, so we have Q here, this amount of heat, and then we can have here in terms of temperature. So of course, the reason, if you look at here, the ice cube is not 0 degrees Celsius. So why does it's important to whether to know whether the ice is at 0 degrees Celsius or not? Because 0 degrees Celsius is the melting point. It means that in this case, the ice, when it absorb energy, when you add up ice inside the water, it is not necessary, it's not going to melt right away. Okay, in conceptual, and what happened here, the ice will increase in temperature first. So here we're going to be negative 15, and then it continue to increase in temperature while maintaining in ice form until it reaches 0 degrees Celsius. When it reaches 0 degrees Celsius, then it's going to melt. So what happened during the melting process is that the temperature is going to be the same. it will remain constant. And then after all the ice has melted away and become water, then that water will still at 0 degrees Celsius. Okay, then after it receive more heat, what happened? Then the water going to increase in temperature, and then what happened eventually? If it eventually reach what we call a boiling point, which is 100 degrees Celsius, then the water will start evaporating at the same temperature, which is 100 degrees Celsius, until all of the water has completely evaporated at 100 degrees Celsius. Okay, where is it? Okay, 100 degrees Celsius. Okay, and then only then, as soon as all of the water has been completely vaporized into a water vapor, it's not going anywhere, it's still within the means that the mass is still the same. It's only that the phase is have changed completely from water to vapor. And then if we continue to heat up this vapor that is been vaporized from that water just now, then we will see that the steam or the vapor will start increasing in temperature beyond the boiling point just now. But at the moment everything has completely, just at the moment that the water has been completely vaporized, the vapor will have will start, before it increase in temperature, it will start at 100 degrees Celsius. Then if you continue to heat up, then it will increase further in temperature and beyond 100 degrees Celsius. Okay, coming back to this. Okay, so what we have here, again, we try to imagine, as I mentioned, all of this, we are not supplying any heat, and then we are not considering that if insulated, so you're not considering that any of this heat that is currently available will be going anywhere. So what we have here, going to have ice, we're going to have ice, and then we're going to have water together. So we know that because of this, there's a temperature different in temperature, there going to be heat transfer between these two, but there will not be any heat transfer outside of this system, nor outside or inside of the system. So what we're going to have here, we're going to have a process where Q ice. Okay, so Q ice, what do you mean Q ice? Q ice is the heat transfer when it is still in ice. Okay, so then after that, what happened to that after the ice? So Q ice here is this side, Q ice. So if it have more energy supplied by the water, we don't know, it will melt. So when it melt, we're going to have Q ice melt. Okay, and then after all of them melt, and then we're going to have Q ice just now, the same amount of the mass is now Q ice water. I mentioned water, Q ice, because this water came from an ice, because we have another water here which is initially is already in a form of water, in a form of liquid. Okay, so to avoid confusion when you assign value to it. Okay, so what we have here, Q ice, and then Q ice. Okay, Q ice. So this one, because for this one is Q MC del T. So then whether it absorb or lost energy, it is described by the change of temperature. So we do not to provide any positive or negative sign, because the change of temperature, if it means that if it from low temperature to high temperature, of course you're going to absorb the energy. If it from low and from high temperature to lower temperature, of course you're going to dissipate and heat energy. Okay, so it means that if it, let's say, from 100 to 50 degrees Celsius, so you're going to dissipate energy. Then if you do this, this is from 100 to 50, so it means that you're going to be 50 minus 100. So of course, because of this, you will get a negative 50. So this will provide you a negative notation, means that the the ice here is going to dissipate uh, uh, its uh, its energy, not ice, this object from 100 to 50 means that it's going to dissipate its heat to other things, and it's going to lose its heat because of the negative sign. But whenever we see something is become hotter, which means that from, let's say, from 20 degrees Celsius to let's say 50 degrees Celsius, then if we know that this object definitely going to absorb. So by this equation itself, it's also going to we can also see the outcome indicating the same observation that we already understood, from 20 to 50. Of course, you're going to need to absorb energy. Then based on the equation here, if we have the final temperature is 50 minus 20, then this will give us a positive value, a positive Q. A positive Q means that it absorbs energy. A negative Q means that it's going to dissipate energy. Okay, so if you look at here, coming back to here before we go to another side, so we are still at the MC delta. Then if you look at this graph, this label here, Q, to the direction of positive, means that in order for it to go from a negative 15 degrees Celsius of ice towards a boiling of steam there, it required to absorb energy, a positive Q. Okay, a positive Q. So it means that everything here definitely need to be positive, because if you look at here, if you zero is the final temperature, from negative minus 0 minus negative 15, it will give you positive value, a positive Q. From 0 to 100 also it will give you a positive Q. Okay, it means that for Q ice melt here, Q ice melt, which is depends on the latent heat, which is MLF fusion. So this thing does not have a temperature, so then we need to indicate sign. So since that this is in order to melt, it need to absorb the energy. By mean of absorb energy, you're going to have a positive Q here. A positive Q means increase in energy. Okay, absorb energy. That object absorb energy, so it means positive is positive flow into the object. But if it a negative flow, means that the object become colder because of the heat is being dissipated. So then it indicate a negative Q, negative Q value. So here, because it is moving to the right, the process is moving to the right to the positive Q, so then this value ML should be left as positive. Okay, so going to that, then we will have that first is M ice, is because this is from the ice, C for ice, and this is specific heat for ice, and then the change of temperature of the ice. So the change of the temperature of the ice, do remember here, it is starting from negative 15 to this is not minus, to 0. So then the operation for this delta, the change of temperature, should be 0 minus 15. Okay, then the next step is that it is going to melt process, melting process, and presumably it's going to melt because 25 degrees Celsius above melting point. So presumably that the amount of water is enough to melt the ice. Okay, then after that, so we in this process, the first point is a process where the ice is at negative 15 degrees Celsius towards 0 degrees Celsius, which is the first incline here. Okay, and then the second step is the horizontal line here, means that the melting process, which is given by MLF. So should we left it to be positive? Yes, because if you look at here, the process is towards the right, towards a positive Q. Okay, so then what else? So then after it melt, it going to, if completely melt, so this is still ice, the mass of ice just now is the same ice of this. So because remember, the label is to help us not to confuse with another water that is already in the liquid form. Okay, so once this ice is already completely melt after receiving this amount of energy, then this ice going to turn into a liquid. So liquid then ice, because it is referring to the mass of ice just now, but the specific heat here is water, because it's already melt into water. And then the change of temperature here would be the final temperature, which is from 0 towards, because why is 0? Because it's just this water, it just melt from the ice, and then it should have the temperature of melting point. Okay, although that all of the ice will melt, but that water, after it melt, it will have the melting point temperature. Okay, and then this 0 will reach to a final equilibrium temperature, the TF, which is the operation for del T would be TF minus 0. Okay, so here for this case you can retain as in a form of Celsius, although that Celsius is not the SI unit, but you can use it because it's the change of temperature, then you can use Celsius. Okay, so then after that, so I think we should have done we should stop here, not continue to further so we are at this point, last time just now we are at that point. We don't need to continue to this point because the water, the heat supply is only at 25 degrees Celsius. Okay, so it means that we've done the ice process. So right now it is on the water side. Okay, on the water side. So the water, what happened to the water? The water technically going to go to what I call that, a cooling process, but we don't even need to put any sign, because as I mentioned, because this water is only going to a change in temperature. Okay, so this is water, so because this is the mass of the water, so before this we do the ice. Okay, so mass water, then the change of then the specific capacity, also water, and then the last one is the temperature change. Okay, the temperature change here of the water, it is from the temperature it provided here in the question is 25. Okay, so it means that it's going to 25 degrees Celsius towards the final equilibrium temperature. So you don't even consider whether you're going to increase or decrease. You just like that, because if this is the process, it's not minus, this is 25 towards final temperature. So this approach is not necessary to be decrease in temperature or increase in temperature. You can apply for both. Okay, but then for this equation, the operation for del T here would be TF minus 25 degrees Celsius, and then all of this should equal to 0, because I mentioned before there's no heat going into, there's no heat going out of the system. Okay, so solve this, you will left with only TF, the unknown variable. You should get the answer, inshallah. Okay, so so this is a different, that one you try out that equation, whether you got it or not. I try to make it short. Okay, so what if in the different situation where the question also going to ask is kind of similar the process, but in this case we will ask like, if a 20 gram of ice at negative 15 degrees Celsius, or I think you have this question, I think already explained before, but never mind. The question is something like this: how much energy required to melt a 15 gram of ice at negative 15 degrees Celsius into steam at 110 degrees Celsius. Okay, so if you look at it, is how much of energy. So how should we illustrate here? So we're going to illustrate the same thing. We have a box. It's a system. It's a system that you try to imagine a box. This is a system. Then inside the box here, we only have one thing, which is ice. We only have one thing here. ice at negative 15 degrees Celsius. Then how can we change it into steam? There's no other way beside adding Q here. So here, then the equation as what we did just now, what we did just now here is the same. On the left side here is going to be the same. It's only that here will not be 0, because here that 0 will equivalent to Q. Of course, in this question, that is the Q that we are looking for. So again, the process will be following to where it is. It's negative 15. So of course it cannot melt away, so you need to increase in temperature until it reaches a melting point, 0 degrees Celsius, and then further increase from 0 to 100 degrees Celsius, which is a boiling point, and then maintain again until everything becomes steam, and then increase to the last temperature of 110 degrees Celsius. So what we need to do here is the amount of the processes now. So we have C ice, ice, because it's the same thing. The ice is going to be the steam, so we don't need to label it because we only have one component here, which is ice. So then technically all the mass are going to be the same. So C ice, so this is important because it increases in temperature based on the specific heat capacity of ice, and then change of temperature is from negative 15 to 0, and then going to be melt. Okay, so whether it's positive or negative, in this case it is going to be positive because it's a positive Q. So if you do the illustrate here, and then you know how the process is, then it should be safe. Okay, and then here they're going to be MLF. So plus, so we have done this, and we have done that, and then the next one is from water. So again the same M, only this is water. Okay, so here it is the equation is 0 for the final temperature minus initial temperature negative 15. Okay, so this delta. So what is going to be this temperature? It is from 0 to 100. So we're going to be 100 minus final minus 0 the initial is just melt from 0 degrees Celsius, and then after that we're going to have MLV, vaporization latent heat, and then we're going to have mass of when it becomes vapor. So this is vapor, V, vapor, and then the change temperature here, I think you can guess it should be from 100 to 110. Yes. Okay, so the final temperature should be 110 minus 100, because it's left with 100 degrees Celsius just now. Okay, so this is the so this what we did before here is equal to 0 because it does not receive heat, but here we are looking how much heat need to go inside here in order for it to become steam. So then this will become Q. It's not 0. Okay, because this technically we require heat from the outside. Okay, so that's how it is. Okay, so try out, get the answer, and then if you do have any question, let me know. Okay, thank you very much.